Welcome to part 3 of Module 4 in Genomic Selection, where we're looking at whether genomic selection is working by reviewing results in the literature. Again, we're looking at 3 different schemes to assess whether genomic selection works, and we have primarily right now looking at scheme number 2, where you have a training population and a prediction populations are different sets of lines, often phenotyped in different environments. So here's another example of scheme 2. This is looking at various traits in winter wheats, and this is a project that was done by one of my grad students, and we're preparing the manuscript. And what we have here are 2 sets of lines. We use one set of lines as the training population, and then a second set of lines as the prediction population, and then we switch the roles of the line. So set 1 is sometimes used as a training population, and then we reverse it and use it as a prediction population. It consists of 200 elite wheat lines from 8 different breeding programs. You can see the details of how it was phenotyped and how it was genotyped, with 4,000 SNPs from the Illumina array. Set 2 consists of 300 current elite wheat lines from 6 different related breeding programs, and you can see the details on how it was phenotyped as well. It's important to note that there's a lot of environments here, but we can do that because this is a cooperative trial, and it's genotyped with the same markers as set 1. And here is our plan for how we tried to assess the accuracy of genomic selection. Set 1 of lines, you already described it, is phenotyped in a certain set of environments and genotyped. Set 2 of lines consists of 300 different lines, and they're phenotyped in different environments. So in the first scenario, we build a model using data from set 1, and that's our training population, and then we can see if that model can predict the values, the phenotypes of lines in set 2 that are obtained from testing them in its second set of environments. The second scenario, we just reversed the first one. We use set 2 of lines and the data from those sets of environments to develop the prediction model, and then we can see if that model can predict the phenotypes of lines, of set 1 lines, that are obtained from a second set of environments. Let's see what some of the results are. We'll start out by looking at results from cross-validation within each population, which is scheme 1. And along the x-axis we have the accuracy we obtained by looking within set 1 lines for the different traits, and the y-axis is the accuracy we obtained by looking in assessing genomic selection within set 2 for the same traits. So for example, we look at the trait plant height. It has pretty high accuracy in both populations. This is a quality trait number 2, pretty accurate in both populations. But some are quite different. The accuracies are quite different in each of the 2 populations. Here's test weight, high accuracy in set 1 of lines, but just a moderate accuracy in set 2 of lines. And yield is always one of the most difficult ones to predict their values, and it was fairly low in both sets of lines. Now let's see what happens if we use data from one set of lines to predict the phenotypes of the lines in the second set. And that is shown here for each of the traits. And this is just an average of the 2 comparisons that we could get. So we look at grain yield. On average, the accuracy for grain yield using one set of lines to predict the values of the others was extremely low. But for traits like test weight, height, maturity, the second quality trait, the genomic selection model built in one population was able to predict the phenotypes in the other one with a reasonable degree of accuracy. And you have to remember, you look at some of these correlations and say they're not that great, but do remember that phenotypic correlations between lines in different environments also is always that great. So here our correlations were greater than 0.3 for all traits except for grain yield, flour protein, and the 5th quality traits. It's important to note here that the lines in each of these sets are related, but set 2 is not a direct descendant of lines in set 1, and of course vice versa. Now the LD patterns, the pattern of linkage disequilibrium amongst the markers in the 2 sets, was actually very similar. So what we conclude is there appears to be a fair amount of marker effect by environment interactions, and these are probably quite high for grain yield, flour protein, and the fifth quality trait. And that's why one population really cannot predict the other one very well. Okay, and when we look at grain yield, flour protein, and the fifth quality trait, their accuracy was actually fairly low in the first set of lines anyways. And one thing we noticed, we look at the accuracy of set 1 and its ability to predict set 2, and the accuracy of using set 2 lines to predict set 1, and you see there's a strong relationship. If one set can't predict the other, then the opposite is also true. The second set cannot predict set 1 if set 1 cannot predict set 2. And if both sets are, and particularly for grain yield, again, it was very low. Let's look at another scheme 2. This is a work done on tetraploid alfalfa. You can see the publication here. And the way they did this is they created a training population, which they called cycle 0, and they created this population by looking at lines derived from crossing three different parents. From those crosses, they derived 100 random plants and they intermated them, so they get a good recombination. And from those matings, they derived 190 plants from those matings. Those 190 plants were then phenotyped, and they are the training population. The trait they were looking at was biomass, and they did this at 3 different environments with 14 total harvests of biomass. And you can see the information here in the genotyping. They use genotyping by sequencing. Now this is a tetraploid. They only scored SNPs that had at least 11 reads. They scored homozygotes, the 2 classes of homozygotes. And heterozygotes, there's many possible different heterozygotes in a tetraploid, and they simply scored them all as heterozygotes, not to try to distinguish between the different classes of heterozygotes. And they were able to call about 9,000 SNPs. Just to show how their assessment scheme 2 worked diagrammatically. Here is their training population. There's C0, as they called it, the 190 individuals, phenotyped and genotyped. And that information is then used to build the genomic selection model. From those 190, they selected 20 that were the best based on phenotypes and intermated them. And this is why I'm calling this scheme 2. They did not do selection based on genomic selection values. They did their selection based on phenotypes. They then derived what they call the C1 population, and this will be their prediction population. They have a bunch of individuals in there. They're phenotyped and genotyped at 3 environments and 8 harvests. And so they'll build the model from this data set and use it to predict the phenotypes of individuals in the C1 prediction population. The first thing they did was look at cross-validation. Accuracy estimated by cross-validation, so that's really scheme 1. They did that within cycle 1 plants, and they also did it within cycle 2, cycle 0 plants, and then within cycle 1. They looked at accuracy of genomic selection within environments, and then in these blue bars you see the accuracy of genomic selection using data from one environment to try to predict the phenotypes that occurred in the second environment or different environments. And one thing you notice is that accuracy of genomic selection is greater when you do it within a certain environment than when you try to use data from one environment to try to predict the other. And this is undoubtedly due to the genotype by environment interaction between the different environments. So now here is accuracy assessed by scheme 2 using data from cycle 0 plants to build the model and see if they can predict the phenotype of the cycle 1 plants. And one thing you note here is that the accuracies here using scheme 2 to assess genomic selection are considerably lower than what we do when we do cross-validation. And this is really to be expected. We have mentioned before that using scheme 1 cross-validation to assess the accuracy of genomic selection probably gives you an upward bias of how effective genomic selection will be. And scheme 2 and later scheme 3 are certainly the more realistic assessments of the accuracy of genomic selection. So conclusions: accuracy is greatest within environments, and accuracy is lower when the training population and prediction population data comes from different environments. And accuracy is lower yet when you use cycle 0 data to predict cycle 1 phenotypes. But they were still optimistic about using genomic selection, and really these results do give you reason to be optimistic. And they looked at it this way: one cycle of phenotypic selection in alfalfa for biomass takes 2 to 5 years, and one cycle of genomic selection can be done in 1/2 year. So your relative efficiency on a per year basis actually comes out quite favorable for genomic selection. On a per year basis, the gains from genomic selection would be about 1.6 to 4.0 times greater than if you did phenotypic selection. We'll continue this in the last part of Module 4.